So in this video we're going to move on from the graphical methods and look at how we can use the data gathered in an experiment to determine orders of reaction and hence find the rate equation. So we're not going to be plotting a graph now. This also forms part of a required practical that you'll be studying. So it's called the initial rates method. It's where you measure the rate for something that can happen very, very quickly at the start of the reaction. So maybe there's a colour change. Maybe you measure a certain volume of gas. You'll have done this method before. The disappearing cross is an example of this method. You're measuring the time taken for that cross to disappear. That cross should disappear at the same molar quantities every time. So you're measuring the lengths of time it takes for that cross to disappear when you've varied the conditions. And in this case we're varying concentrations. So to do this method you would keep one concentration the same and just vary one. And you might keep one of the concentrations much bigger than the other in order that it is staying the same, because actually it's quite difficult to make sure that one of them stays the same while the other is varied. So you might keep it much bigger. You could then plot concentration time graphs to find the initial rate, although you can do a much quicker way of finding a measure of the initial rate by just finding 1 over time, and that's going to give you a measure of the initial rate, although it's not going to give you the exact rate, it's going to give you the idea of the value. So how would you use data from an experiment looks like this to determine order? So what we're going to do first of all is we're going to try and find the order with respect to A. Now to do that we need to find somewhere in this table where A changes but B doesn't, so that we know that any effect we're measuring is down to A alone. So what we would do is we would find somewhere where A is the only one that changes, and if we have a look here we can see here that A is changing but that B is not. So we can see that A is changing, it's times by 2, but that B is not. Okay, so A is doubling but B is unchanged. So if we're comparing experiments 1 and 2, B is constant, that's quite important, but A has doubled. And because this is a mathematical thing, I'm just going to write times 2, because that's the mathematical way of saying it's doubled. And what has happened to the rate? So we'll go over here and see what happened to the rate between experiments 1 and 2. Now on your calculator you take the second number and you divide it by the first number. So you type in 1.6 times 10 to the minus 2 and you divide it by 0.4 times 10 to the minus 2. If you do that you'll see that that is multiplied by 4. So the rate has quadrupled. And as we go through these you'll find that these numbers, these words become harder to write, and that is why it's useful to write them in mathematical just in terms of multiplied by 4. And then we have a look. What we're trying to do is remember that the rate equation has some sort of rate is in some way proportional to A to some power. And we want to find out this relationship. So we've said our rate is multiplied by 4, but A was multiplied by 2. We just need to know what the power is. So 2 to what power equals 4? So 2 to what power equals 4? So you have to think, well, what would I need to do? And the answer is that I would need to square it. So we'd say that that power is a 2, and we'd say that it's second order with respect to A. So now we need to find the order with respect to B. What we need to do for that is find somewhere where B changes but A does not. So if we have a look now, if we look at experiments 2 and 3, we can see that B is changing but that A is staying the same. So if we have a look, that A is staying the same but B is doubling, and rate, we can type that on our calculator, we can see that that is doubling also. So if we compare experiments 2 and 3, A is constant and B has times by 2, B has doubled, and rate has also times by 2. So what we need to do now is think, if our rate is proportional to our B to some power, our rate was times by 2 and our B was times by 2, to what power 2 to what power is the number 2? Then it must be first order with respect to B. So what we're going to do now is we're just going to move up and we're going to try and put that into a rate equation. So just remember we had that the rate is always equal to the rate constant K times the concentrations to their orders, and A was second order and B was first order. So what's the overall order? Remember the overall order is the sum of the orders, so it's 2 add 1, first add second, which is 3. Can you rearrange that video to find K? So pause the video and rearrange that equation to find K. So there you go, I've rearranged it to say K is rate over A squared B. It says insert the values from any experiment. It's quite common to use experiment 1, and the reason you can do that is you won't get that sort of number displacement. If you use the top line, you're picking all the numbers off the top line. So we're going to put those numbers into our expression, and we're going to put in the rate on the top, which was 0.4 times 10 to the minus 2. And then we're going to put in the concentration of A on the bottom, which was 2 times 10 to the minus 2 squared, and then B, 2 times 10 to the minus 2, but not squared for B. Now use your calculator, use that fraction button, so press the fraction button, fill in the top line, fill in the bottom line, remembering to square your concentration of A. And if you've done that right on your calculator, you should have got 500. Now we're going to work out our units. Now remember that the units of rate are moles per decimetre cubed per second, and they are in the table. And the units of A are moles per decimetre cubed, because it's concentration, and B, moles per decimetre cubed. So what you'll see there is we've got 1 concentration per second on the top, that's rates, and we've got 3 concentrations on the bottom. So we've got concentration to the minus 2, and so concentration to the minus 2 would be moles to the minus 2, dm to the plus 6, and then we have the seconds to the minus 1. Once you've got that value of K, you could use it to find out a new rate. So remember that our rate equation went rate equals K A squared B. So we knew that K was 500 and that A is 0.2, and we know it's squared, and then we know that B is 0.5, and we can put all that into our calculator and come up with an answer. If you do that, what answer do you get? Should have got 10 moles per decimetre cubed per second. So we're going to move on to have some other questions on this. So what I'd like you to do is to pause the video and see if you can work out the answer to this first example. So if we look at the first one, I've chosen experiments 1 and 2. I can see that J is staying constant, so if I want to find the order with respect to hydrogen ions, I can see that when J is constant, the hydrogen ions half and the rate goes down by a factor of 4, so quarters. You just put the second number on your calculator, so 3, and then divide it by 12, and it will come out as a quarter. 0.25 over 0.5 comes out as a half. A half to what power is a quarter? And what you'll find is that a half squared, you just can practice, if you're not sure on these fraction powers, just practice putting the number in and typing in to the power 2, to the power 3. You've got a limited choice of orders, so just try different numbers and see which one works out. Now because to make this little sum here work, a half to the x equals a quarter, x must be 2, we know that it's second order with respect to hydrogen ion concentration. So pause the video again and see if you can work out J. Now it's a little bit more tricky because there is nowhere where H stays the same. So because there's nowhere where H stays the same, it doesn't matter which 2 lines you pick. I'm going to pick, really doesn't matter, I'm going to pick experiments 1 and 3. That's times by a half from 1 to 3, and that's times by 2, and rate is times by 2. So what I'm going to do is I'm going to say that from experiments 1 and 3, J is times by a half. Hydrogen ion concentration is times by 2. And rate is times by 2. Now what we know is that rate, which was our times 2, is equal to, just get rid of the times because we don't really need it, is equal to, the order for H plus was 2, was multiplied by 2, and we know already that the order for H plus is squared, so I can put that in, times by the effect that J is having, which is a half, and we don't know what the order is for J. So H we knew is second order, so I put in H was doubled and it's second order. So I'm going to do a little bit of maths on this, rearrange this. So I know that 2 equals 4 times a half to the x now. I'm going to divide both sides by 4, so I'll get 2 over 4, which is a half. A half equals a half to the x, then x is first order with respect to the concentration of J. Okay, so what I can do now is build up my rate equation to say that rate equals K times J to the 1 and H plus squared. And it doesn't matter which order you put these things in because multiplication is irrespective of that order. See if you can rearrange and find a value for K with its correct unit. So pause the video, see what you can come up with. So there you go, I got 240 and I've worked out my units, remembering that rate is concentration units times seconds to the minus 1, and if it's overall third order we've got 3 lots of concentration on the bottom, so that's the same as concentration to the minus 2, or moles minus 2 dm6, seconds minus 1. So here's another one. Pause the video again and see if you can work this one all the way through to the end. So if you've worked that through, you should have found that it was second order with respect to m. I chose lines 1 and 3 to find n, where m has times by 4 and n is times by 3 over 2. But you could have picked a different 2 lines. The only 2 lines you couldn't pick would be 1 and 2 because n didn't actually change in lines 1 and 2. But say that I picked lines 2 and 3, what difference would that have made? So let's just have a look. If we'd have picked experiments, put the right pen on, experiments 2 and 3, instead that then m would have been times by 4 over 3 and n was still times by 3 over 2, and this time rate was times by, and we need to just get our calculator out and figure out what rate was times. And if you type 2.4 and divide it by 1.35, what you'll see is that your calculator says 16 over 9. So if you did that, you did 4 over 3, and we know that m is second order, so squared, times by 3 over 2, but we don't know what the order for n is yet, so that's our unknown x, equals 16 over 9. Now if you type 4 over 3 into your calculator and square it, you will get 16 over 9, so you get the same idea. 3 over 2 to the x equals number 1. The only way to make that work is to have a power 0. So whether you'd picked lines 1 and 3 or lines 2 and 3, you will get the same answer. And if you want to check your working out at any point, work out your rate constant K using 2 different lines, and if you get different numbers, you've probably gone wrong somewhere in your rate equation. So that's the end of this video using the initial rates method. I would suggest you find some more examples in your study pack or one of your exam packs and you practice that in a bit more detail.